All right, this is going to be a review of exponential functions. So an exponential function is a function where the input variable x is the exponent. This type of function is used to model patterns that increase or grow, or decrease or decay proportionally, or by a constant percentage or ratio. An easier way of thinking about these patterns is that they are being repeatedly multiplied by a constant value, in contrast to linear functions, which are repeatedly being added by a constant value. So they always appear, well, I don't want to say always, but the simplest form, standard form, is y equals a times b to the x, where a represents some initial value, and b represents the growth or decay factor, basically what you're multiplying by, and x represents the number of times you multiplied that initial value, or the number of times the initial value has grown or decayed. And when you evaluate all of that, you get the output or the resulting value y. So we can use the model above to write exponential functions to model data. So let's take a look at the following data. We've got an initial value with an input of 0. We get out a 2. So 2 is our initial output. Then when you input 1, you get out a 6. Input 2, output an 18. Input 3, you get out a 54. So in linear functions, we used to find a common rate of change. But here we don't have a common rate. Here we're increasing by 4, then we're increasing by 12. So the slope does not remain constant. But if you notice, all right, if you multiply 2 by 3, you get 6. If you multiply 6 by 3, you get 18. And if you multiply 18 by 3, you get 54. So, using our model, our initial value would be 2, and our growth factor, or what we're multiplying with, would be 3. So the initial value is 2, and the growth factor is 3. So we could write the equation y equals 2 times 3 to the x to model this data. Let's see if it works. Let's plug in a 0. 3 to the 0th power is 1 times 2 is 2. 3 to the first power is 3 times 2 is 6. 3 squared is 9 times 2 is 18. And 3 cubed is 27 times 2 is 54. So this equation does model the data in the table. Let's take a look at the next one. Here our initial value is 128. Now it seems like we're getting smaller here. So can we be multiplying? We must be dividing, right? Well, as we went over in the beginning of the year, we can think of every division problem as a multiplication problem. So it would seem like we're repeatedly dividing by 4, and we are, but exponential functions represent repeated multiplication. So what is the multiplicative equivalent to division by 4? That would be multiplication by its reciprocal, 1 over 4. So 128 divided by 4 or multiplied by 1/4 is 32, multiplied by 1/4 is 8, and multiplied by 1/4 is 2. So here our initial value was 128. Our growth or decay factor, in this case it's decaying since it's getting smaller, is 1/4. And so once we identify those, we can plug them into the standard form of an exponential function, and we get y equals 128 times 1/4 to the xth power. And if you plugged in your inputs, these are the outputs you would get. So let's try this on your own. Here are two sets of data. What I'd like you to do is identify the initial value and the growth or decay factor and see if you can write an exponential model on your own. Pause the video now. All right, let's see how you did. So in the first model, all right, we started out with our initial value was 5, and we kept multiplying by 4. So if our initial value is 5 and the growth factor is 4, then our equation should look like y equals 5 times 4 to the x. In the second one, it wasn't as clear. So we had to create a ratio or come up with a value that we could multiply 40 by to get to 60. All right, and if you make the ratio 60 to 40, that simplifies to 6 over 4, which simplifies to 3 over 2, and that you could represent as 3/2 or the decimal 1.5. So here our initial value is 40, and we're repeatedly multiplying by 1.5. So once you identify those values, you can write your equation y equals 40 times 1.5 to the x. And one more example so that you can see this repeated multiplication in action. What do you get when you take 3 and you double it 6 times? Let's try to write an equation to model this situation. So pause the video now. Let's see how you do. So one way to look at this is you're going to get 3 times 2 6 times. If you're doubling the value 3, then you're multiplying it by 2, then you're multiplying it by 2 again, and again, and again, and again. And as you can see, when you write this repeated multiplication in exponential form, this looks very much like our exponential function, where we have an initial value, and we're repeatedly repeatedly multiplying an x number of times. In this case, we're starting with 3, and we're repeatedly doubling or multiplying by 2 6 times. And you can see those the different parts of the function here. So now, how do we graph exponential functions? There's no easy way like we have in linear functions. For linear functions, all you need are 2 points, because 2 points are enough to define a line. Once you have those 2 points, you just connect them and extend the segment in both directions, and you get your line. But with exponential functions, they're nonlinear, they're curved, and how many points do you need in order to graph a curve? Well, the answer is you need an infinite number of points, but if you're just looking to sketch one, then you need, as I said in class, enough. And what's enough? Enough is enough data points to identify the contour or the shape of that particular function. So in this case, I'm going to input -6, -4, -2, 0, 2, 3, and 4. All right, and when I do that, I get the following values. And when I graph those points, I get something that looks like this. Now, if you notice, because the growth factor, or what we're multiplying, all right, is 2. All right, when you multiply by a value that's greater than 1, your initial value, in this case, although it's not written, it's an invisible 1 here, is going to get bigger. It's going to get larger. 1 times 2 is 2, 2 times 2 is 4, and so on and so on and so on. So we'd expect this function to increase because its growth factor is greater than 1. And sure enough, it's increasing. And it looks like it's going to increase or continue to increase and go up into infinity, getting faster and faster and faster, or growing faster and faster as x increases. But as x decreases, it looks like these values are getting very, very close to, they're getting smaller and smaller and smaller, but they're never going to go to the negative side. They're getting very close to, but never quite reach 0. So now let's take a look at, and when we sketch our graph, it looks kind of like this. All right, and this is the general shape of all exponential functions. Looks kind of like an L or a hockey stick, but the important features are one end goes off into infinity, and another end kind of flattens out at a certain point. In this case, it's going to be 0. Later on in the year, maybe we'll learn about different functions that don't flatten out to 0. And in Algebra 2, you will definitely expand upon this model, and you'll see exponential functions that look very like this, but they're flipped. They're going the other way. The main point that I'm trying to say is they don't always have to flatten out to 0, but they do have to flatten out to something. Okay. Let's do y equals 1/2 to the x. And remember, there's an invisible little 1 here. So you can think of this as 1 being multiplied by 1/2 or divided by 2, all right, repeatedly an x number of times. So what would we expect this to be? Would this, if you multiply something by 1/2 or divide by 2, are your values going to get larger or are they going to get smaller? All right, and the answer would be they're going to get smaller. So if your growth or decay factor, in this case your decay factor, is less than 1 but greater than 0, basically a number between 0 and 1, then your values are going to get smaller. And this is reflected in the graph using these data points. When we graph that, if you notice, as x increases, y gets smaller and smaller and smaller and flattens out here at 0. So one end goes to infinity and the other end flattens out at a certain value, in this case 0. All right, let's use the function to solve some real-world problems. So number 1, let's say we had 5 bacterial cells and they're placed in a petri dish. If each cell replicates or doubles 8 times per hour, how many cells would be in the dish after 1 hour? What about after 2 hours? So there's 2 questions here. What we need to do is identify the different parts of the function. In this case, if we want an output, we're going to need an initial value, a growth or decay factor, and the number of times that we've grown or decayed. Here we have an initial value of 5 bacterial cells. So we're going to put 5 where A is. Each cell replicates or doubles. It looks like we're multiplying by 2, so that's going to be our growth factor. And we do that 8 times per hour. And if we do that 8 times per hour, so, well, x is going to be 8 for 1 hour. And for 2 hours, all right, it's going to multiply 8 times for the first hour, 8 times for the second hour, so that would be a total of 16 hours. So our 2 equations should look like this. 5 times 2 to the 8th, that's replicating 8 times for 1 hour. You'll have 1,280 bacterial cells. But after 2 hours, notice, all right, we're raising 2 not to the 8th power, but it's going to be 8 times for the first hour, 8 times for the second hour, so that's 2 times 8, so that's 2 to the 16th, and that gives us 327,680 bacterial cells. A lot more bacterial cells than after the first hour. All right, so for number 2, why don't you try number 2 on your own so you get some practice using the model, and we'll see how you do. Pause the video now and do your best. All right, there was some extra information in number 2. You might have noticed that. So let's read through it. A bank pays an interest rate of 5% per year, which means at the end of the year, your balance will be 105% of your balance at the beginning of the year. If you deposit $100 and don't withdraw any money, what will your balance be after 10 years? So let's start to identify the different parts of our model. What's our initial value? What was the initial balance of the account? That would be $100. Now, what is our growth factor, or the value that we're multiplying by? You might have been tempted to say that it's 5%, but that is what's called the growth rate. It says an interest rate of 5%. The growth factor is the value that explains, it's basically a ratio between what you have now and what you had or what you started with, all right? Or it's what you end up with after multiplying. So at the end of the year, after increasing by 5%, what do you end up with? Well, that would be 105%. So we're going to plug in 105% or 1.05 into our growth factor. And of course, we're going to do this 10 times, so our x is going to be 10. And so what we get is 100 times 1.05 raised to the 10th power, and that gives us approximately $162.89. All right, try number 3 on your own. Let's see how you do on this one. All right, so pause the video and we'll be back soon. All right, let's see how you did. This one was a little tricky. A car loses 10% of its value every year. All right, now is 10%, well, let's read through the problem. If the original price of your car was $15,000, what would be its value after 10 years? So let's see what we're doing. We're taking $15,000 and we're taking 10% away every year for 10 years. $15,000 is our initial value. But how could we take 10% away? Well, if you remember from class, taking 10% away from a value is the same as having 90% of that value. Because if you take 10% away, what are you left with? 90%. And since the growth or decay factor in this case, since we're getting smaller, all right, represents a ratio of what you have to what you had, well, what do you have after 1 year compared to what you had? You have 90% of your original value. What about the year after that? You retain 90% of that value, and so on and so on and so on. Remember, the factor, or the growth or decay factor, tells you what you end up with. All right, not exactly, it doesn't necessarily describe exactly how you're changing. So our growth factor would be, our decay factor would be 90%. And of course, we're doing this for 10 times for 10 years. So our equation would look like this: $15,000 times 90%, or 0.90, all right, raised to the 10th power, gives us $5,230.18. All right, here's more of a challenge problem. You're going to encounter this in your assignment today, so pay lots of attention. Read through the problem and see if you can come up with the right answer. Now, I'll give you one hint. As you read through the problem, ask yourself, what parts of the model can I fill in? Once you do that, all you have to do is find the unknown value. Pause the video now. All right, let's see how you did. Let's read through the problem. When a value A is doubled 17 times, it equals 589,824. What is the value of A? So the first thing that strikes me is this problem is about A, the initial value. So that variable is going to be left blank. We don't know it. It's unknown. So in order to find the value of A, we're going to need the growth or decay factor, the number of times it's grown or decayed, and the resulting value or the output. So let's read the problem again, and let's see if we can find those values. When a value A is doubled, so what are we doing to A? We're multiplying it by 2. How many times are we doing it? 17 times. And when we do that, it equals 589,824. So it looks like we're given the values of B, the growth factor, X, the number of times we're growing, and Y, the value that results. And what we want to do is solve for A. So when we fill in those values, we get 589,824 equals A times 2 to the 17th. If we simplify 2 to the 17th, we get 131,072 times A. All right, and now all we have to do is divide both sides by this whole value, and what we get is A equals 4.5. If you got that on your own, excellent job. If you didn't, that's all right. This one was a little tricky. It kind of breaks the mold of the problems that came before it. All right, so we're going to now build a model for exponential growth and decay, and we're going to use these functions to model real-world situations. So you may remember this from class. Julie wants to buy a beautiful new lamp for her living room. The price of the lamp is $45. The sales tax in Maryland is 6%. So what is the total cost of the lamp with the tax included? All right, now there are two approaches, two ways that you can figure this out. All right, you can think that the total cost is going to be 6% more than $45. So in order to find that, you'd have to find 6% of 45, which is going to be $2.70, and then add that to the $45, which would be $47.70. And this is the way most of you were comfortable doing this when we first started this unit in class. That's fine, all right? This is not a wrong answer. However, because we're dealing with repeated multiplication, we simply can't think of it this way anymore. Or at least if you're going to do this repeatedly, you need to think of it a little differently. So if we have 6% more than a value, that's the same as having 106% of that value. So if you want to excuse me, if you want to find 106% of $45, you would just multiply it by 106%, or 1.06, that percentage represented as a decimal. And when you do that, you get the same exact thing. All right, and so you also might remember this from class. If we generalize this situation using the variables A for the initial value, R for the growth rate of the sales tax, and Y for the resulting value of the total cost, you get two viable equations. Y equals A times AR, and Y equals A times 1 plus R. And all we've done is use the distributive property to factor out this A to get this second equation. All right, and you'll see why this second equation represents this second approach, and this first equation represents this first approach. And this second equation is the model that we're going to use and build upon. So here we have our model. The resulting value is equal to the initial value times 1 plus the rate of growth. And the rate of growth tells you how your value is changing. Is it going up by a certain percentage, or is it going down by a certain percentage? So let's take a look at this in the context of a real-world problem. Alyssa took her family out to dinner. The price of the meal was $78.50. She decided to leave an 18% tip. What was the total cost of the meal, tip included? All right, let's use the model we just derived. So our initial value, excuse me, is $78.50, and she decided to leave an 18% tip, so she's going to increase that value by 18%. Our initial value goes into A, and 18%, we substitute that in for R, the rate of growth. All right, so that would look like $78.50 times 1 plus 18%, or 0.18. All right, simplifying that, what we get is $78.50 times 1.18, and that gives us $92.63. All right, let's take a look at a second situation. Julie went back to the store a week later and saw that the lamp was now on sale for 25% off. If the original price of the lamp was $45, what is the new price? All right, so in this case, we're decreasing the value by 25%. All right, so we could take the same two approaches. We could think of this as 25% less than $45, in which case you'd have to find 25% of 45, which is $11.25, and take that away from $45, and that gives you $33.75. But, like I said, there's a different way of thinking about these values. If you have 25% less than $45, that's the same as describing 75% of $45. And so if you multiply $45 by a ratio of 0.75, then what you get is $33.75, the same as you would get over here, because these are equivalent processes. All right, and using the same approach to generalize this to all situations, we get a very, very similar set of equations. Y equals A minus AR, and Y equals A times 1 minus R. So using this second equation that we're going to build upon, let's use that decay model and apply it to a real-world situation. So Alyssa got a job at a restaurant. As an employee, she is entitled to a 10% discount on all purchases. She decides to take her family out for another meal. The normal price of the meal is $84.75. With the employee discount, how much will Alyssa pay? So here, $84.75 is our initial value, all right? And our rate of decay, because it's a discount, is going to be 10%. Or you can think of it as, a rate of decay is always negative. So if we're decreasing the value by 10%, then we're taking away this ratio. All right, so this is going to be negative 10%. And when we plug that into the equation, what we get is 84.75 times 1 minus 10%, all right, which would give us 84.75 times 90, and that's equal to $76.28. All right, now, let's try to apply this to a situation that requires repeated multiplication. So we've got Akakik Bank, and it pays its depositors an annual rate of 5% interest on their savings account. If you put $100 into a savings account, what would the balance be after 1 year, 2 years, and 3 years? Use the model to find the answers and write them using a function table. So our initial value is $100. To find the balance after 1 year, we take 100 and multiply it by 1 plus the growth rate, 5%, which would be 1.05. 100 times 1.05 equals $105. So now our balance is $105. All right, so to find the balance after 2 years, what we take is our new balance and increase that by 5%. So we'd multiply it by 1.05, and that gives us $110.25. To find the balance after 3 years, we're going to have to increase this new balance by 5%. So we do the same multiplication again. $110.25 times 1.05 gives us $115 and $0.7625. I didn't round here because we'd lose precision, and you'll see why, because we're not going to stop at year 3. So my question to you is, would this be an efficient method if you needed to find the balance after 35 years? And as we discussed in class, this would not be an efficient method. Why? Well, in order to find year 2, we needed to know the balance of year 1. In order to find year 3, we'd need to know the balance of year 2. In order to find year 4, we'd need to know the balance of year 3, and so on and so on and so on. In order to get to the 35th year, you need to go through all of the other years. That's 35 calculations that you don't want to do. So let's see if there's a better way. So one thing we can do is we can rewrite this using substitution. So we know that let's look up here. 100 times 1.05 is equal to $105. So instead of writing the $105 here, we could just write the calculation that gets us there, which is 100 times 1.05. All right, so that's what I've done here. Here's our $105, and all we're doing is taking that and multiplying it by 1.05, and that gives us $110.25. All right, now all I did was put all the calculation for the second year, and I added on another multiplier of 1.05, and I hope you can see what's happening here. All right, if we were to write these expressions in exponential form, they'd look like this. 100 times 1.05 to the first power, 100 times 1.05 to the second power, which just means we're multiplying 1.05 twice, and 100 times 1.05 to the third power. All right, and extrapolating this, we can see that to get to the 35th year, we just take the initial balance, $100, and we'd increase it by 5% or multiply it by 1.05, and we do that 35 times, and that would get us $551.60. And from this, all right, we can use this information to build upon our growth and decay model. When growth or decay occurs by the same percentage or ratio multiple times, this is called exponential growth or decay. And so now our model is just like our growth and decay model, but now we've added our little exponent to represent repeated growth or decay. And just remember, the value of r is positive when we're growing, and it's negative when we're decaying. All right, now let's compare and contrast the two different models that we've gone over so far. So they're both the same model. Here's y equals a times b to the x. And the second one that we just derived is y equals a times 1 plus r to the x. All right, here the value of b, okay, is just expressed as 1 plus r. All right, where b is the growth or decay factor, and the growth or decay factor is, or it tells you what the initial value is being multiplied by, or what percentage you end up with after growing or decaying once. And the growth rate, all right, tells you by what percentage your initial value is changing. So these are just two different forms of the same thing. The value b is actually equal to 1 plus or minus, if r is negative, r. So let's try to use this model in a real-world situation. In 1985, there were 285 cell phone subscribers in the town of Centerville. The number of subscribers increased by 17.5% per year after 1985. how many cell phone subscribers were in Centerville in 2005. So let's see. In order to use this model, we're going to need an initial value and a growth or decay rate. So the initial value is 285 cell phones. So we're going to plug that in for A. All right. The growth rate was 17.5% per year. So we're going to plug that in for R. And I'm sorry, we need one additional value, X, the number of times we've grown. And in this case, we want to know how many cell phone subscribers were in Centerville in 2005, which is 20 years after that initial value in 1985. So our equation should look like this. Y equals 285 times 1 plus 0.175 or 17.5%, all right, raised to the 20th power. Simplifying that, we get 285 times 1.175, all right, raised to the 20th power, and that's 7,171 rounded to the nearest whole number. And as you can see, all right, this 0.175 represents the rate of growth, whereas 1.175 represents our growth factor. When we increase a value by 17.5%, we end up with 117.5%. All right, during normal breathing, about 12% of the air in the lungs is replaced after one breath. Write an exponential decay model for the amount of the original air left in the lungs if the initial amount of air in the lungs is 500 milliliters. How much of the original air is present after 240 breaths? All right, so our initial value is 240. All right, that goes right there for A. All right, now our decay factor, in this case, our decay rate is 12%. So every time you breathe, from that original, set of oxygen atoms, or the air. It's not just oxygen, but that's what we care about. Anyway, 12% is replaced, so it's a new 12%. So we're losing 12% every single time we breathe. So we're decaying by 12%. So we're going to put in a negative 12% there, and we're doing this 240 times. I'm sorry, did I say 240 was our initial value? I'm sorry, I meant to say 500 milliliters is the number, or is the amount of air that we're starting with. Negative 12% is going to be our decay rate, and we're doing this 240 times. Sorry about that. And so our equation should look like this. Y equals 500 times 1 minus 12%, and we're going to do that 240 times. All right, simplifying this gives us 500 times 0.88%, all right, which is equivalent to 1 minus 12%, or 100% minus 12%. Because if you have 12% less of a value, all right, then you have 88% of that value, or you're left with 88% of that value. So if we do that 240 times, that gives us approximately 2.4 times 10 to the negative 11th, which looks like that, or a really, really small number, basically 0. All right, and one last problem for this exponential growth decay model. The population of Winnemucca, Nevada, can be modeled by the equation P equals 6,191 times 1.04 raised to the T power, where T is the number of years since 1990. What was the population in 1990, and by what percent did the population increase each year? Well, the population in 1990 would be our initial value, so that answer there would be 6,191, all right? And by what percent did the population increase each year? Well, here we have 104% as our growth factor. Now, if we split that up into 100 plus the growth rate, that would be 100 plus 4%. So it seems like we're adding 4% every year. So the answers would be the population was 6,191, and the population increased by 4% per year. All right, here are 3 problems that you can work on your own. Work through all 3 of them, and I'll go through the answers when you're done. Let's pause the video now and do the best you can. All right, let's see how you did. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. If we start with only one bacteria which can double every hour, how many bacteria will we have by the end of one day? So, if we start with only one bacteria, so that means our initial value is going to be 1. All right, now we're doubling it. When we double, all right, we're multiplying by 2, but if we're using this model, we have to think, what is our growth rate? Well, when you double, how much do you increase by? You might say you multiply by 2, but that doesn't tell me what percentage you increase by. All right, so if you're doubling, if you start with 100%, all right, what do you end up with? Well, that would be 200%. You increase by a whole 100%. You increase by your whole value. So, plugging that value into the model, we get one bacteria times 100% plus another 100%, because we're increasing by the whole value, 24 times, because there's 24 hours in one day, all right, gives us 1 times 2 to the 24th power, which is 16,777,216. All right, the second one. You have inherited land that was purchased for $30,000 in 1960. The value of the land increased by approximately 5% per year. What is the approximate value of the land in the year 2011? So here our initial value is $30,000. All right, we're increasing this value by 5% per year. All right, and we're doing this for, I believe, 51 years. All right, so $30,000 would be our initial value. Our growth rate would be 5%, and we're increasing by 5% 51 times over 51 years. And what we get is 30,000 times 1 plus 0.05, raised to the 51st power, which gives us this in simplified form. And when we use our nifty little calculation devices to simplify this expression, we get $361,223.09. Don't forget that 9 cents. All right, and finally, an adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in the person's system decreases by 29%. How much ibuprofen is left after 6 hours? You can round your answers to the nearest hundredth. So in this case, we're starting with 400 milligrams of ibuprofen. So that's going to be our initial value. We're decreasing this value by 29%. So our decay rate is going to be negative 29%, or negative 0.29. And we're doing this 6 times over 6 hours. All right, so our equation should look like 400 times 1 minus 29%, or 0.29, and we're doing that 6 times. All right, when you take away 29% of a value, you're left with 71% of that value. So if you take 71% of 400 6 times, that gives you 51.24 milligrams.